Everyone, as you know that I am doing strength of material previous year questions, which is directly from the exams like GATE, IES and IAS. I have already completed 20 videos, so if you are new in this channel, please watch those videos as well. Okay, so today we are going to see GATE questions, okay, which is from bending moment and shear force diagram. So in short, we say that SFD BMD. Okay, so this will be helpful for those students who has strength of material as a one of the course, like for the mechanical engineering students as well as for the civil engineering students. Okay, so both can take advantage of this. Okay, so let's see GATE questions. Okay, so here some diagram is given. Okay, so here in this the force is acting into the paper, you can say into the paper. Okay, inside the paper, if there is circle and dot, then it is out of the paper. Let's read the question. SFD BMD question. A concentrated force F is applied perpendicular to the plane, as I told you. Okay, of the figure. On the tip of the bent bar as shown in figure, the equivalent load at a section close to the fixed end. Okay, so they are asking what is equivalent load here. Okay, if we applied load here inside into the plane, so the force, what will be these forces, I mean that force. Okay, equivalent force. So options are force F bending moment FL and bending moment FL. Okay, force F and twisting moment FL, force F bending moment FL and twisting moment FL. Okay, so we have to tell like what are the equivalent loads are acting here. So see, obviously, like if you apply inside, I mean force, you can say, I mean perpendicular or into the plane. So what happens, this thing will be actually it will twist and there will be force F. I mean bending moment will be there, I mean not bending moment, twisting will be there. Okay, because if you are perpendicularly, if you are applying even out of the plane also, if you are applying, so it will be the same thing. So there will be twisting moment, okay, as well as this force F, both will act here. Okay, so here the answer will be force F and twisting moment F into L. So okay, so the answer is C. So please remember here, so force F and twisting moment. Next question. The shear force in a beam subjected to pure position bending. Okay, so there was pure positive bending, not position bending, pure positive bending. See, this is like filling the blanks type of question. It is like very old question, like 1995. So that time there was filling the blank kind of question was there. But nowadays you will not find this kind of question. But actually you have to put the data. Okay. So earlier it was like that. So it is positive, 0, negative. So okay, so the answer for this is 0. Please remember this. Okay, next question. This is cantilever. You can see this half part is cantilever. Okay, so let's read the question. Two identical cantilever beam are subjected as shown with their free ends in contact through a rigid roller. After the load P is applied, the free ends will have. Okay, so they are applying force here, I mean okay, load here. So after applying applied load P, the free end will have. Okay, so what they are asking, what will have, free end, what will have, equal deflection but not equal slope, but not equal deflections. Okay, so equal slopes as well as equal deflection, neither equal slope nor equal deflection. Okay, so free end, they are asking the free end what will have. So what happened here, actually it will have equal deflection but not equal slope. Okay, so this is the answer. Because as it is a rigid roller, deflection must be same. Because after deflection they also will be in contact, but slope unequal. Okay, so slope will be unequal, but they will have equal deflection. Equal deflection. So the answer is A. Next question. Let's read that. So this diagram is given. A beam is made up of two identical bar AB and BC. Okay, so this will be actually B. So AB BC by hinging together at B. Okay, so here it is hinged, at B this is B. So here it is hinged. The end A is built in cantilever. Okay, so end A is built in cantilever and the end C is simply supported. Okay, so this is cantilever, so here they have connected one more hinge, so I mean more support, so that is nothing but simply supported. So that's why it is simply supported with load P acting as shown in figure. So here P is acting, the bending moment at point at A. So they are asking here, okay, here at point A, what is the bending moment? So this is the diagram. Here is hinge. So at the C, it is simply supported. This is, here is the cantilever. They are applying force P. So they are asking what is bending moment at A. So see, this is actually standard case. Actually, what will happen here? Here actually the bending moment is PL by 2. Okay, this is a special kind of diagram. So please remember this. Okay, so for this the bending moment diagram at the bending moment at A will be PL by 2. Next question. Cantilever with a uniformly distributed load. Okay, so based on this topic, they have given the question. Let's read that. The shape of the bending moment diagram for a uniform cantilever beam carrying a uniformly distributed load over its length is. Okay, so the shape of bending moment diagram for a uniform cantilever beam carrying uniformly distributed load. Okay, so over its length. So what will be the bending moment diagram? So a straight line, hyperbola, ellipse, parabola. Okay, so we'll see. See, so this is nothing but cantilever. This is a cantilever. It is, uniformly distributed load is there. Okay, so this is uniformly distributed load. So if you draw bending moment for this, it will be a parabola. Okay. Anyway, you can think like how it is parabola. So if you write equation for bending moment, the equation will be this. Okay, so it is nothing but it is a parabola. You can see the equation, it is a parabola. So the answer is D. See, after once I will finish the previous year question, then I will come up with the theory part of strength of material. Okay, so there I will derive for all kind of loading. This I will draw the bending moment and shear force diagram for all kind of loading. Okay, so once you watch those lecture as well, so this question will be very easy for you. Okay, so if you are like BTech student, so I think you have already done this thing in your BTech. Okay, so no problem. As of now, you just remember it is a parabola. Okay, later I will explain like how this is coming, so you can easily tackle this kind of questions. Okay, no problem. Next question. Again, it is like this kind of loading. So they are asking a bending moment diagram. Yes, a cantilever beam carries antisymmetric load shown where omega, what load, you can say that W naught is the peak intensity of the distributed load. Quantitatively, the correct bending moment diagram for this beam. Okay, so actually this is cantilever. So this load is something acting like this. Okay, here the half part, it is something like that. Okay, and a rest half part, it is something like that. Okay, something like that. So if you remember, like, previous question, it was uniformly distributed, but here it is uniformly, I mean, it is varying, the load is varying. So in this case, what type of uh, BMD will be there? Okay, so I think you can answer this question from the, by seeing, this option. So what happened, this is, you can see that for this is nothing but this is the thing. Okay, so what we have to do here, for see, the answer will be D. Okay, so again, if I'm going to draw here these I mean derived relation and all those things, it will take a lot of time. Okay, so anyway, in the previous question I told you, like, once I will start the complete lecture series of strength of material, so I will come up with the how to draw stress, I mean also not stress, shear force diagram and bending moment diagram for different type of loadings. So there we'll see in detail like how this type of graph is coming. So as of now, you just remember, so the answer will be D. Okay. Next question. So it's based on simply supported beam carrying concentrated load. Okay, no problem. We'll see that a concentrated load of P acts on simply supported beam of span length A L at a distance of L by 3 from the left support. Okay, the bending moment at the point of application of the load is given by. Okay, so these are the options: PL by 3, 2 PL by 3, PL by 9, 2 PL by 9. So this is actually diagram based on Cuny statement. So it's a simply supported beam. So here the force is acting P at a distance of L by 3 from the left support. Okay, so it is like L by 3 from the left support. So in this case, the bending moment is nothing but PAB. It's standard formula, PAB by L. Okay, so this A is L by 3 is given from left. It is L by 3. So this will be 2L by 3 since length is L. So if you put all these value here, so PL L by 3. Okay, B is 2L by 3 L. So if you simplify, you will get 2PL by 3. 2PL by 9. Okay, so the answer is D. Okay, so these things actually we'll see how these things are coming, like how this MMC is PAB by L. So as of now, you remember this is the type formula, but later you will derive this. Okay, next question. Okay, let's read that. A simply supported beam carries a load P through a bracket as shown in figure. The maximum bending moment in the beam is. Okay, so this is the diagram. Like, so here the force is acting. Okay, this is L to this is 2L, this is L, this is A. So they are asking the maximum bending moment in the beam. So in this case, what is the bending moment that they are asking? Okay, they are not asking the diagram, they are asking the value. So here, see, so first of all, we have to calculate the reactions. So you can see here, if we apply force here, so it will give the moment. It will give a moment of P by A. Let the force is P. Obviously P is given. So if you apply force here, so it will give a moment of P by A. You can see here. Okay, so let's say here RA. So just to take a moment. Okay, so if you take a moment, then you can take from any side, like you can take from here, okay, or you can take from here, from any side you can take a moment. So if you take a moment, so actually you have to take moment from once from this side, another from this side. So you'll get a two equation. Okay, so let's say first equation is this. So you will get RA and RB. Okay, in terms of P. Okay, so obviously here P will also be there and moment is also there. So you can do with your own. Okay, so first take moment from this point, another from this point. So if you simplify this, you'll get RB is this, RA is this. RA and RB is reactions at point here and at point here. So once you get this, so take a moment, write a, maximum bending moment at the center. Okay, so here will be the maximum bending moment, that is nothing but at point C is RA into L by 2, so this is L by 2, okay, plus P into A plus RB into L by 2. Okay, so there is three forces are acting, this one, okay, and obviously see from this C, this PA actually from this point we are taking, so the C is acting, P is acting on this point itself, so we will not consider that moment, so only we'll consider this one P into A, okay, because this is passing through this point, so we'll not consider that. So there will be, for whole diagram there is, three forces will act, four moments will be there, one for this, and one for this. So these all forces, these all moments actually we have to add that. So RA into L by 2, plus P into A and RB into L by 2. This is also L by 2. Okay, this is actually BMD of this kind of force. So if you have to put this RB value here and RA value here. Okay, so if you simplify, you will get PL by 2 plus PA. Okay, so what is the answer here is C. Okay, so this type of question is little bit lengthy kind of, but we have to do is very fast in the exam. Okay, this will be obviously 2 marks question. So what you have to do first, calculate the reaction and take a write a moment equation at point C, okay, and get the answer. So this is the thing. Okay, so anyway, this is end of the, I think, second part of BMD. I think first part of BMD will go, I think, many parts. So thank you for watching. Bye bye.